Hi everyone, in this video we're going to look at some naturally occurring phenomenon that can be modeled by the exponential function where b is greater than 1. Now remember that for an exponential function, like let's say y is equal to let's just say y is equal to b to the power of x, that if b is greater than 1, then the function looks something like this, where the graph approaches a horizontal asymptote, and then the function continues to increase quite rapidly. And as the function continues to increase, its rate of increase actually increases. So this graph just keeps getting steeper and steeper as x increases. So this growth in the y value is actually called exponential growth. Now we're going to define some other things, like the doubling period. The doubling period is the time it takes for a given quantity to double its size. So things that that can be modeled by the exponential function have a constant doubling period. That is, the amount of time it takes for them to double in size is constant. That means that, like, let's say, I have 200, a quantity of 200, then a quantity of 400, then a quantity of 600. Quantity of 200, 400, and then 800. Or I'm just doubling the quantity each time. This change let's actually make a table of values. So if this were y and this were x, let's say that our x value was x1, x2, and x3. Well, this change in x would actually be constant, and then we'd be doubling y for every time that we increase by this constant change of x. Let's just call this, I don't know, like delta x. Delta is often used for change in math. Those of you that took grade 9 academic math know that delta x means the change in x, and we use this when we're calculating slope. So when the change in x is the doubling period, the quantity here for y, or the y value, should double. So delta x here would be the doubling period, the amount of time that it takes for the quantity to double. So in this example that I have written out here, we're told that the bacteria of a certain type are known to double in population by dividing every 20 minutes. And here it says, suppose that there are 300 bacteria at the start. How many bacteria will there be after 2 hours? So at the start, there's 300 bacteria. So let's say the number, let's let n represent the number of bacteria. And so let's say that n of let's write n is equal to 300 times 2. So it doubled. How many times did it double here? Well, if it doubles every 20 minutes and 2 hours went by, and we had 300 bacteria at the start, how many times did it double? So how many times does 20 minutes go into 2 hours? Now remember that 2 hours is actually 120 minutes, and if we divide 120 minutes by 20 minutes, we get the number of doubling periods. So 120 divided by 20 is just 6. So we have to multiply this by 2 6 times. So let's go ahead and we'll do 300 times 2 to the power of 6. And we get that this is equal to 19,200. So therefore, there will be 19,200 bacteria after 2 hours. Here it says after T hours, how many bacteria will there be? So here it actually wants us to write an equation for like a general equation for T hours, not just specifically 2 hours in this case. So here let's let n of t represent the number of bacteria as a function of time. As a function of time t, as a function of, let's say as a function of time t in hours. And so let's think about this. Well, I've got n of t. I know that every time that 20 minutes goes by, I'm going to multiply 300 by 2. So I've got 300 times 2, and I know that I'm going to have some exponent here. So let's think about what I should have in the exponent. Now I want this in terms of hours. So every time 20 minutes goes by, I want to multiply 300 by 2. So what that means is that, let's think about this. If I just raise this to the exponent t, and t is in hours, when 1 hour goes by, I would have had just 300 would have just doubled once. But I want it to have doubled 3 times. So I need to multiply t here by 3. So I'm going to have 300 times 2 to the power of 3t. And then it says, how long will it take for the bacteria to reach 9,830,400? So here we can let n of t be equal to 9,830,400, and then I can solve this equation for t. So I've got that that's equal to 300 times 2 to the power of 3t. I've got this equation now, and I can solve it by first dividing both sides by 300. So I can divide the right side by 300, and I can divide the left side by 300. And if I do 9,830,400 divided by 300, I get 32,768. Well, that's equal to 2 to the power of 3t. Now, the next thing that I can do is I can raise, if I wanted to try to isolate this, I can raise both sides to the exponent 1/3. And let's see what that does for me. If I raise the right side to the exponent 1/3, on the right side of the equation, I get 2 to the power of t, because 2 to the power of 3t to the power of 1/3, I'm just going to multiply the exponents, because when I have a power to a power, using the exponent laws, I multiply the exponents. 3t times 1/3 is just t. On the right side, I'm raising 32,768 to the power of 1/3, and that's the same thing as just taking the cube root of 32,768. So if I take the cube root of this number, I get 32. Now, here we've got 2 to the power of t is equal to 32. I can rewrite 32 as with a base of 2, because it's just 2 to the power of 5. So I have 2 to the power of 5 is equal to 2 to the power of t. And here, in order for the left side to be equal to the right side, t has to be equal to 5. So therefore, it will take 5 hours for the bacteria to reach 9,830,400.